Hello everyone, I welcome you all for the 8th session of the chapter Ray Optics. In our previous session, we had discussed about the refraction of light through the prism and we obtained a relation which is relating the refractive index of the prism with its angle of the prism and angle of minimum deviation. Well, in this class, we will be studying about the important phenomenon which is related to the sunlight. Okay. So, as you know that a sunlight is a composite light, correct? So, what do you mean by a composite light? Composite light means it contains 7 different colors in it. Okay. White light is having a different ranges of wavelength, so which is ranging from 400 nanometer to 670 nanometer. A white light or a composite light is traveling in air or vacuum. So, when this composite light is traveling in air or vacuum, the 7 different colors of light is traveling with the same speed, because air or vacuum is not a dispersive medium. So, all the colors of light are traveling with the same speed. Now, let us say that we have a prism here, this is a prism, and this white light is now entering into a prism. So, white light is consisting of 7 different colors of light, and this white light is now entering into a prism. Prism is a dispersive medium. What happens here is this incident light, which is a composite light, will splits into 7 different colors inside the prism like this. So, the 7 different colors of light are splitting like this. Okay, and while traveling out of the prism, so we can see 7 different colors in this. Okay, so this is V I B G Y O R. So this is nothing but a VIBGYOR, means a white light or a composite light which is traveling in a non-dispersive medium like air. All the colors of light are traveling with the same speed, so we cannot distinguish the colors. But when it is entering into a prism is a dispersive medium. So when it is entering into this dispersive medium, what happens is this composite light splits into 7 different colors. And while coming out of the prism, we can see all those colors. So the colors are nothing but VIBGYOR: violet, indigo, blue, green, yellow, orange and red. So this is called as a spectrum. Okay, this is nothing but a spectrum of colors. This phenomenon is called as a dispersion of light. So this phenomenon is known as dispersion of light. Okay, so what is dispersion of light? When a composite light enters into a dispersive medium. Remember, prism is a dispersive medium. So when a composite light enters into a dispersive medium, it splits into 7 different colors. So this phenomenon is called as a dispersion of light. So in nature, we can see this dispersion of light in the form of rainbow. So what is the reason for the formation of rainbow? The formation of rainbow is because of the dispersion of light by a spherical droplets of rainwater. That is what we need to understand now. Let's understand it. See, a rainbow is an effect of a dispersion of light by a spherical droplets of rain. Okay, or we can say that the formation of rainbow is due to the combined effect of dispersion of light and refraction through the spherical droplets of rain. Okay, what is the condition for the formation of rainbow? The condition is when sun is shining at the one end and there is a rainfall at the other end. Okay, so there is a rainfall at the other end. So here we can observe a formation of rainbow from this side. So we can observe a formation of rainbow at this end because the sun is shining on the other end and the rain is falling on this end. We can see the rainbow always on the other side where there is a sunshine. So we have 2 types of rainbow, primary rainbow and secondary rainbow. So what are those? First, let us understand how does a primary rainbow is going to form. A primary rainbow. So here we have a sunlight. Imagine a ray of light from the sun is incident on the spherical droplet of water or a spherical droplet of rainwater. So here what happens is a spherical droplet of water is nothing but a dispersive medium, just like a prism. So when white light, a sunlight is entering into this droplet, what happens is the colors are going to split. The red color, which is having a longer wavelength, bends the least, and the violet color, which is having a shorter wavelength, bends the most. And while coming out of this spherical droplet, so this is a violet light, we can observe a violet light here, and we can see this red color like this. So for an observer who is observing from the incident direction of light, you can see a violet color at the top and red color at the bottom. The angle subtended by this red light is 42 degree with respect to an incident direction, and the angle subtended by the violet color is equal to 40 degree. So this is how a rainbow is going to form in nature. When composite light enters into a spherical droplet of rain, so this is a dispersive medium, and the light is going to split into 7 different colors, and we had written only 2 colors here, but we have 7 different colors in it. So the red color bends the least because it is having a longer wavelength, and this violet color bends the most because it is having a shorter wavelength. So after coming out of the droplet, we can see the violet color on the top and red color at the bottom. So if you find the angle subtended by the red color with respect to the incident direction, which is 42 degree, and for the violet color it will be 40 degree. Okay. So I told you that this phenomenon is because of the both dispersion and a refraction of light. So how does a refraction takes place here? If I say that this is a spherical droplet of water, when the light is incident into this spherical droplet of water, first at this surface light is going to refract like this. Okay, light is going to refract like this. So here the angle of incidence is more than a critical angle, therefore the total internal reflection takes place here. Okay, so at this point a total internal reflection takes place, and the ray will be reflected to the same medium. The refraction again takes place here, and that is how we can see a rainbow. So a rainbow formation is a 3-step process, correct? It's a 3-step process. First refraction takes place here, then a total internal reflection here, and again a refraction here. So it's a 3-step process. Refraction, then it is followed by total internal reflection, and finally while coming out of this, again one more refraction. Okay, so the formation of a primary rainbow is a 3-step process. First it happens to be a refraction, then it is total internal reflection here, and then a refraction again at this point. Okay, so this is how a rainbow is going to form, or a primary rainbow is going to form. Now let us understand how does a secondary rainbow is formed. Imagine a sunlight is falling in this direction, and here somewhere we have a rain which is falling in the vertical direction. So here at this point the light is going to refract into a spherical droplet of water, then here a total internal reflection takes place and the light is reflected to the same medium like this. Next again one more total internal reflection takes place here, so that the light is entering again into a same medium. Now at this point the light will comes out in this way. Okay, here in this case it is a 4-step process. See, first the light is entering into a droplet, so refraction takes place at this point, and here a total internal reflection is taking place. Here again one more total internal reflection, and finally at this point the light is coming out. So this is how a secondary rainbow is formed. Now while coming out of this, a red color will appear at the top and a violet color at the bottom. So if you find an angle, so if you observe from this direction, you can observe that red color is having an angle of 50 degree and violet color is having an angle of 53 degree with respect to the direction of incident light. In the case of a secondary rainbow, red color is at the top which makes an angle of 50 degree and violet color is at the bottom which makes an angle of 53 degree with respect to the incident direction. So this is a 4-step process. Let's write that. It's a 4-step process. First a refraction here, then 2 total internal reflection, 2 total internal reflections, and finally a refraction, and finally a refraction. So this is how a secondary rainbow is formed. Now what is the difference between the primary rainbow and the secondary rainbow? In case of a primary rainbow, violet color is at the top and red color is at the bottom. But in the secondary rainbow, red color is at the top and violet is at the bottom. A primary rainbow is a 3-step process where refraction takes place, then a total internal reflection, and finally a refraction again. And in the case of a secondary rainbow, it is a 4-step process. First a refraction followed by 2 total internal reflections, and while coming out of this, it is a refraction. So it's a 4-step process. Fine. So those are the basic differences between primary rainbow and a secondary rainbow. Now we'll move on to the next concept. The next topic is about the optical instruments. So under that, we'll be studying the 2 important optical instruments which are microscope and a telescope. Okay. So we are not going in detail with this microscope and telescope. We'll be just writing the ray diagram for the microscope and telescope and also their magnification produced. Okay. First, let me take a microscope. Under that, we have a simple microscope. Simple microscope. A simple microscope is nothing but a converging length of smaller focal lengths. So you know what is a converging lens? A converging lens is nothing but a convex lens. A convex lens with a lesser focal length or a small focal length makes the simple microscope. So the aim of using this simple microscope is to see the virtual erect magnified image of the smaller objects. So let us draw the ray diagram for this simple microscope. So you know that a simple microscope is nothing but a convex lens with a smaller focal length. Let us draw a convex lens with principal axis, and for this convex lens the focal length is very shorter. So here somewhere we have a focal length. So this is called as a focal length F, and towards this side also we have a focal length F. Okay. Now in order to see the objects which are very smaller with a magnified view, we have to place the object within this focal distance. So let us place the object, a small object, at this point, and we have to see the magnified view of this object. So how do you see this? We have to keep our eye very close to the lens so that we can see the magnified image. So how does the image is going to form? First I will consider a ray which is incident parallel to the principal axis, and this is aperture of the lens, and this ray will be refracted in this way, correct? And now one more ray which is incident along the optical center will travel like this. Now if you observe these 2 rays, so these 2 rays are almost diverging from each other, so that we have to retrace them back to get the image. So I am retracing the path of this ray. So I am getting somewhere here, and let us retrace this also, and we will get somewhere here, and somewhere at this point the 2 refracted rays are joined together. Now you can draw an image here, and this image is a virtual image with a magnified one, correct? So this is a magnified image. See, the object is shorter and the image is longer, which means the image is magnified or it is enlarged. To see the magnified view of the smaller objects, we are going to use this convex lens. So here somewhere we have an observation, point of observation, and if you observe from this point, you can see an image at here. So this distance can be called as a D, which is called as a near point or a least distance of distinct vision. For normal eye, the least distance of distinct vision is 25 centimeter, and the magnification produced for this image will be equal to M is equal to 1 plus D divided by F, where F is the focal length of this lens. Suppose if I have a focal length of the lens as some 5 centimeter, if you substitute to this formula, we'll get M is equal to 1 plus D is 25 centimeter. I already know this. So this is 25 divided by 5. So that this can cancel, 1 plus 5, M is equal to 6. So we get an image which is magnified 6 times. Okay. So when I have a lens which is having a focal length of 5 centimeter, we can see the object which is magnified 6 times. So this is how you can see the smaller object with a magnified view using a convex lens, and this is nothing but a simple microscope. Okay. Well, so the simple microscope can be used only to produce a magnification of around 6 or maximum of 9. But for further magnification, if I want more magnification, we should go for the next instrument, which is nothing but a compound microscope. So let us understand how does compound microscope works. In compound microscope, we have two lenses which are placed coaxially. So how does they looks like? See, the first lens is called as an objective lens, which is having a smaller focal length, and the second lens is a eyepiece, or which is also called as a eye lens, eyepiece or a eye lens, and this lens is called as objective lens. This is an objective lens. So both these lenses placed coaxially so that they are having a common principal axis. Okay. Now let us say that the focal length of this lens is FO, which is at this point. Now let us place an object behind the focal length so that with this lens forms a real image. Let this is the incident light, and which is refracted in this way, and one more ray is refracted in this direction, so that the two refracted rays are joined at this point so that an image is formed here. Okay. Image is formed. An inverted real image is going to form here. Well, the image is formed by the objective lens is this. Now, the position of the eyepiece is so adjusted that the focal length of the eyepiece is more than this distance. That is the distance from this image to this lens. So, for this eyepiece, this image which is formed by the objective lens acts as a virtual object. The rays which are emitting from this virtual object are made to fall on this lens like this. As this object is kept within the focal length of the eyepiece, the two refracted rays will be divergers. The two refracted rays will diverge from each other. See, this is how they diverge from each other. Okay. Now, if I produce these two diverged rays in a backward direction, if I retrace them in a backward direction, somewhere here they can meet. Okay. Then near the object, an image which is a magnified image is going to form. So this is how compound microscope works. Okay. So it consists of two lenses. One is called as a objective lens, other one is a eyepiece. They are placed coaxially. So when an object which is kept behind the focal length of the objective lens, it forms a real image here. So this real image now acts as a virtual object for this lens. The position of the eyepiece is so adjusted that the focal length of the eyepiece is more than this distance. Now the rays which are emitting from this object is made to fall on this, and the two refracted rays will be diverged. And if I retrace them in backward direction, somewhere here an image is going to form. So this is nothing but a final image, and this is a object. How do you find the magnification in this case? The magnification produced by the compound microscope is a multiplication of magnification produced due to the objective lens and magnification produced due to the eyepiece, MO into ME. But we can find that the magnification produced by objective lens is equal to L divided by FO. So what is this L is? L is nothing but the distance between the two lenses, which is nothing but the length of the tube of the compound microscope. So L divided by FO into this ME, the magnification produced by the eyepiece, that will be equal to D divided by FE. So what is this D? D is the near point or least distance of distinct vision of the eyepiece. So this is D divided by FE. So if I have the focal length of the eyepiece as some 2 cm and focal length of the objective lens as some 1 cm, then we can write, if the length of the tube of the microscope is 25 cm, let us write this as 25 cm divided by focal length of the objective lens is 1 cm into the least distance of distinct vision is 25, you already know this, and the focal length is equal to 2. Say this is 20 cm, not 25, it is 20 cm. So if I cancel this 2 with this 10, so 25 into 10 is 250. So the magnification is equal to 250. Means, so the smaller object can be viewed 250 times magnified using a compound microscope with a focal length of the objective lens as 1 cm and focal length of the eyepiece as 2 cm. Okay. The next one is a telescope. Now what is a telescope? A telescope is an optical instrument which is used to produce the angular magnification of the distant celestial objects. Okay. So this is the use of the telescope. So we have a refracting telescope as well as a reflecting telescope. Phenomena of refraction and as well as a reflection. So both can be used to make this telescope. First let us understand the refracting telescope. So well in telescope we have two lenses again, an objective lens and an eyepiece. They are placed coaxially. An objective lens is having a more aperture and the eyepiece is having a lesser aperture, which is the reverse case of a compound microscope. Okay. Now the rays from the distant object are made to fall on the lens. So let this incident ray is making an angle of alpha here, and they're refracted here, and they're refracted like this, and they form a image here. Okay. So this is the image formed by the objective lens. This is the image which is formed by the objective lens. Now the position of the eyepiece is so adjusted that this distance is lesser than the focal length of the eyepiece. Now what happens is this object acts as a virtual object for this lens, and the rays which are emitting from this object are made to fall on this, and they are going to diverge in this way. They almost travels in a parallel path, and if I retrace these two rays in a backward direction, they will meet somewhere at infinity. So they will meet somewhere at infinity to form an image. So that if I say this is beta, the magnification produced, the angular magnification produced for this telescope, that can be written as beta by alpha. The angular magnification is beta by alpha. So that a distant object, so that can be seen with a angular magnification. Okay. This is how a refracting telescope works. And we have one more type of telescope which is called as a reflecting telescope and also called as a Cassegrain telescope. So that works in the basis of a reflection of light. So let us understand that. So this consists of, this is a tube with, at this point we have a mirror. Okay. So here we have a primary mirror. Now when the rays are falling on this mirror, parallel rays from an infinite distant object are made to fall on this mirror, and they will be reflected in this way. They will be reflected in this way, and here at this point we have a secondary mirror which is a convex mirror. So for this convex mirror, these rays will be converging in this direction, and somewhere here we can place an eyepiece so that we can see an image here. So here in this case it's a Cassegrain telescope, okay, which is a reflecting telescope. So this is a reflecting telescope. So here we have a primary mirrors. Okay, this is a primary mirror, and this one is a secondary mirror. So this is a secondary mirror. So a light from a distant object are made to fall on this primary mirror so that they will be reflected to this point. And here we place a secondary mirror. So due to the secondary mirror, it's a convex mirror so that it converges the light at this point. So, and here we have an eyepiece. We can observe the distant object at this point. Okay. So in this way, in this case, a reflecting telescope, the resolution is more and the loss of light energy is less. That is why the reflecting telescope is more preferred than the refracting telescope. Because in refracting telescope there may be a loss of energy or the resolution may be less. But in the case of a reflecting telescope, so we can have a more resolution and also there is a less amount of energy loss. So this completes the session and the chapter ray optics. Thank you.